Alright, let's continue. Let me open the table of content first. Okay. We are still in chapter 21, exploring the homework measurement here. Let me open that. Basically, the chapter 21 is about swap mechanism, I guess. Pull out, what is it called? Move the memory into this, or move the memory in this to the memory, I guess, something like that. Yeah, the swap mechanism here. And now we will take a look at this code to simulate the, what is it called? The swap, I guess. But we will also use this vmstat. Basically, what is it called? A virtual memory statistic, maybe something like that. Okay, let me open that. Alright. Yeah, now we will take a look at this. How do the CPU usage statistics change when running map? Alright. I think we can do something like this. Using active and inactive, and then the timestamp, I guess. And maybe we can combine that like this, and then the lay count 10, maybe something like this. This one VM beyond. Okay. Yeah, let's use 1 megabyte here, or maybe byte. Running this one first. Okay. Waiting until it's done. Alright. Oh, okay. The CPU usage statistic when running mem. Yeah, let's check this information, I guess. These are percentage of total CPU time. Okay, time spent running non-kernel code, the US here, and then time spent running kernel code, the SY. I guess this one. Yeah, it's. Why is it not? Oh, what is it called? Why is it not aligned? I am not sure. Is that always the case? Maybe. Interesting. So I remove that. Not really. The one that goes in alignment time is this, I guess. For some reason. Okay. Anyway, let's alright. Well, let's just do without the active or inactive. Okay, SY is time spent running kernel code. IT time spent idle. Okay, this is include. Oh, okay. Prior to Linux kernel 2.5.41. This is includes input output wait time. Okay, but after that I guess we spirit that because we have this one too, the WA time spent waiting for input output. Oh, interesting. So WA also include idle time prior to the Linux kernel version 2.5.41. Okay. Time stolen for a virtual machine. Alright, I guess. I assume this virtual machine is from the QEMU. Maybe something like that. Oh, prior to Linux kernel version 2.6.11, it is unknown. Alright. Time spent running KVM guys code. Okay. Guys time include guys nice. Yeah, if I remember correctly, nice is some kind of scheduling program, I guess. I haven't tried nice program yet, but that is something to keep in mind. Okay, let's check. I think we run the script during this time, right? How do the CPU user statistic change when running mem? Do the number in the user time column make sense? User time column, I assume this one, I guess, non-kernel code. How does this change when running more than one instance of mem at once? Okay. So far is not really much, I guess. Maybe more of consistent. 1, 2, 3. Okay. Okay. I guess starting from this one maybe. Okay. 12. Oh, okay, interesting. So there is some, maybe some spike, I guess, but not that much from the CPU time. Yeah, that make me curious though. 15. Okay. Okay, we are in this segment. Okay. kind of the same. Alright. Yeah, previously I want to try. Okay. Oh. Alright. Yeah, I want to try. I guess this is when we run the mem script, right? The CPU usage. When we run this mem script, and this one is the CPU usage when we are not running the mem script. I assume something like that. Okay. It's not. Well, at least there is some spike in the CPU usage when we use the mem with 1 megabyte of memory, the mem script here, or executable, I guess. Does the number in the user time column make sense? I'm not sure what kind of sense we need to use here. I mean, maybe. Yeah, I mean, how do we know it this makes sense or not? I mean, if the CPU usage on user time here, what is it called? On user time here is 100 or something like that. I guess that doesn't make sense. But maybe in this one this makes sense. Maybe. I'm not sure. And then there is also time spent running kernel code. Oh, that is interesting. We didn't really have some difference when it comes to the kernel code execution, I guess. And then what is the ID? Idle time. Okay. Oh, the idle time decrease, I guess. Time spent waiting for input output. Alright. Nothing changed here. And for the last two here, well, we didn't use virtual machine, so that's why maybe this is 0. Maybe. Okay. So total number in the user time column makes sense. Maybe. How does this change when running more than one instance of mem at once? One instance of mem at once. Alright, maybe let's do this. Okay, alright, start that. Alright. Okay, let's see. I assume the first question here focus more on the CPU usage rather than any usage or other usage, right? And in this one, well, and then the second question focus on two column, SWPT and free. Okay. All right. I guess this is when we run the first script, okay, and maybe this one is when we run the second script. Or maybe this one. Yeah, I should have wait, I guess, for this to appear. Okay, let's try this again. Alright, okay, run that. Waiting. Alright. Okay. This is when we run the first script, and this is, I guess, when we run the second script. Okay, so there is some increase in the CPU usage, but maybe not that much. Maybe, but I'm not sure if, let's say, we prolong the running time, something like that. Let's try, I guess. Okay. Alright. Waiting for the second heater. Okay. Yeah, let's prolong this and see. Oh, 22. Okay. Alright. Okay, what we can see here is that as the user time increase or non-kernel code time increase, the idle time decrease here, right? And then this is when we run the second script, I guess. So it increase the user time, what is it called? The biggest user time spent is 22, I guess, on this timestamp 38. Okay. Oh, but then it decreased. Okay, maybe there are other processes that use this CPU? Maybe. So just so happen there's a spike here. Okay. How does this change when running more than one instance of mem at once? Well, the user time also increase and oh, this is quite interesting. Oh yeah, and I thought the idle time did not decrease, but it looks like the idle time also decrease. Okay, to a certain degree. So here the user time span increase, right, when we run more than one instance for the CPU usage here, and the idle time decrease. So there is that, but I'm not sure if that makes sense or not. Again, what is the point of reference here? At least from my assumption, this is kind of makes sense. I mean, the jump is not too much, I guess, but at the same time, I am not sure how much the jump in the, what is it called, in this time span makes sense or not. And yeah, what measurement do we use here? Is it in second or millisecond? I am not sure. Probably millisecond, maybe. But yeah, I'm not sure the time measurement we use here. Okay, to answer this one, how do the CPU statistic change when running mem? Well, the user time change increase and the idle time decrease, but the kernel time or the kernel code time is kind of the same, I guess. And when we run multiple instances of mem, the user time span also increase. Maybe something like that. Okay, let's now start looking at some of the memory statistics while running mem. Some of the memory statistics while running mem. Should I remove this one? Maybe not yet. Maybe not yet. Okay. We will focus on two columns here. SWPT, the amount of virtual memory use. Amount of virtual memory use. Isn't that the swap memory? I mean, if we are talking about virtual memory, isn't all of this is virtual memory? Yeah, that kind of confusing, I guess. And then free, the amount of idle memory. Oh, wait a minute. Does that mean this what is it called? The buff and gauge here is the amount of physical memory use. Is that what it means? And inactive or active also the what is it called? The amount of physical memory in use. I am not sure. Yeah, why are we calling that virtual memory for SWPT? If this is the only virtual memory in the VM start, but then again VM start itself stand for virtual memory statistic, you know. So I assume all of this is virtual memory, I guess. Yeah, I'm still not sure, but at least I assume all of this is just a virtual memory, and SWPT here is the swap memory, maybe something like that, or maybe the disk space to hold the swap space, maybe something like that, maybe. But anyway, this SWPT is the swap memory, and this free is the idle memory. I assume this is unused memory, right? Because, well, there is also the inactive memory here. It is apparently the memory is still allocated, but it is not recently used, something like that. And there's a high chance that we will deallocate this inactive memory. Something like that. Excuse me. Okay. Run the mem. Okay. 1024, which allocates 1024 megabyte, and watch how this value changes. Then kill the running program by typing Ctrl+C. Okay, and watch again how the value changes. What do you notice about the values? The value on these two columns. I don't think the SWPT changed that much, but well, we will see, I guess. In particular, how does the free column change when the program exits? Oh, does the amount of free memory increase by expected amount when mem exits? Oh, that is interesting. Okay, I didn't notice that, I guess. We have this one. Yeah, let's use 10. Okay, maybe something like this. Let's run this first, and then take a few time cancel this. Okay. Okay, I guess. Oh, the CPU uses kind of spiking. Well, maybe there are other process other than the mem script that we run, right? So the free memory decrease, right? After we run the mem script, and then it looks like when we terminate the script, we have more free memory. Let me check again. Okay. Yeah, this is after we free or we terminate the program, the mem program there. And I guess this is when we start the mem program. See, it increase the CPU usage. Okay. And then after we terminate the program, the free memory here increase, or the idle memory increase. Okay. What do you notice about the value? Well, the SWPD didn't change that much. Maybe because I still have a lot of memory to spare. Maybe. But the free memory or the idle memory change. So when we run the mem program, the free memory decrease or the idle memory decrease. But then when we exit the mem program, the idle or the free memory increase. Okay. Does the amount of free memory increase by the expected amount when mem exits? I am not sure what the expectation here, what the expected amount here. Yeah, so I'm not sure about the answer. But if the expected amount means that we return to the previous idle memory value or amount before we run the mem memory, then maybe not, I guess. I am still not sure why that is. Maybe there are other processes that also being deallocate coincidentally. Maybe. But yeah, we didn't return to the previous idle memory before running the mem program. We somehow have more idle memory when we terminate the mem program here. Is that consistent? I'm not sure. Okay. Alright. not always the case. Okay. Sometimes we have less idle memory here. Okay. So it depends, I guess. This is just so happen, what is it called? Maybe other process also they allocate the memory. So yeah, it is not the same as when we before we run the main program. Okay, something to keep in mind. Now I'm kind of curious about the active and inactive here. Maybe we should check that out too. Okay. Alright. Okay. I guess this is when we exit or terminate the main program, and this is when we run the main program from the looks of this idle memory. Okay. And then what about the inactive here? In the inactive here, looks kind of the same, I guess. Or yeah, maybe there's some small change, but not that much. What about the active here? The active memory here change. Yeah, quite a lot, I guess. Okay, the active memory here increase, right? Maybe quite significant, at least from this number. And then when we terminate the main program, it also decrease. Alright. Okay, that is interesting. Yeah, I'm still not sure how we determine the increase here. Okay, let's continue to question 3. We will next look at the swap columns SI and SO, which indicate how much swiping is taking place to and from the disk, right? Of course, to activate this, you will need to run mem with large amount of memory first. First, examine how much free memory is on your Linux system. For example, by typing OK, get proc mem info, or we can take a look at the manual page proc here for the tiles on the /proc. Okay. Process information. Alright. It is commonly mounted at the /proc. Okay. Typically, it is mounted automatically by the system, but it can also be mounted manually using a command such as mount here. Okay. One one of the first entries in /proc/mem info is the total amount of memory in your system. Okay, let's assume it's something like 8 GB of memory. If so, start by running mem 4000, around 4 GB, and watch the swap in or out columns. Do they ever give non-zero values? Then try with 5000, 6000, etc. What happened to these values as the program enter the second loop and beyond, as compared to the first loop? How much data total are swapped in and out during the second, third, and subsequent loops? Do the number make sense? I'm not sure if trying this out on live stream is a good idea, because I might get the out of memory when trying this out, and then the live stream will cut off. So yeah, I don't think I will try this question. You can try this out yourself on your machine or computer. But here, let me take a look at the proc here. Okay, I guess it's fine. What didn't really have private information or something like that. Yeah, this is the information on my system. I have around 16 GB of RAM right now. The free is maybe around 9 GB, something like that. What is mem available? What is the difference between mem available and mem free? Let's find out. Linux Pro, the difference between mem free and available. Does that mean the mem available is not free or not idle? Yeah, I'm not sure. Let's find out what is the difference here. I'd like to know the exact difference between mem free and mem available. Also, any hint as to how I could more efficiently use system resource would be appreciated. I have a new laptop on order, but for the moment I'm developing on machine with 1 GB of RAM. Oh, okay, this is 11 years ago. Alright, let me copy this in the chat in case anyone wants to take a look. Not I was running to terminal and Eclipse at the time of the comment, so you can see how it's tough to multitask things in advance. Oh, okay. Is programming question. Interpreting the output of a command line utility. Mem available provide estimate available memory. And yeah, that's what I'm curious about. What is the difference between free memory and available memory in this case? Many load balancing and workload placing program checks /proc/mem info to estimate how much free memory is available. They generally do this by adding a free and case. Oh. Program info to estimate how much free memory is available. Free and case, it was fine 10 years ago, but it's pretty much guaranteed to be wrong today. It is wrong because case includes memory that is not freeable as batch case, right? In the, not that one, I guess, this one, the case information in the VM start, something like that. Okay, for example, set memory segment TMP/FS, the temporary file system, I assume, and then RAM/FS. I'm still not sure what RAM/FS is, and it does not include reclaimable slab memory. Does not include reclaimable slab memory, which can take up a large fraction of system memory on mostly idle system with lots of files. Currently, the amount of memory that is available for a new workload without pushing the system into swap can be estimated from memfree, active and inactive, and what is as reclaimable here? System reclaimable maybe, as well as the low watermark from the proc zone info. However, this may change in the future, and user space really should not be expected to know kernel internals to come up with an estimate for the amount of free memory. It is more convenient to provide such an estimate in /proc/mem info. If things change in the future, you only have to change it in one place. Okay, so does that mean mem available is the mem free with the case? Oh, memproc includes the documentation for /proc/mem info. The amount of memory available for starting new application without swapping. Let me check this, I guess. Using mem available is a better estimate than using mem free. On current implementation, mem available can be significantly larger than mem free if there is a large batch case. Okay. Mem available is calculated as this one. of memory available for starting new application without swapping. Then memory the amount of physical RAM in GB bytes, okay, if unused by the system. Definition is not clear enough to user. Is mem available refer to software or even user space? What does application mean? Other than swapping, use space include. What about direct map and kernel page? This again analogy problem. That is to say, the name that can be named is not a constant name. Back to reality, what we really want to know is how to calculate what at least with is bigger. Okay. This is interesting. The mem available is less than the mem free on the ARM-based sample here. Is that always the case? I mean, is it the specific architecture behavior? I'm not sure. But currently we have this one because I have the x86 64 base computer. Sadly, after opening to only base server, the problem is more complex, CPU related. When we go to restaurant, sometimes there are free tables, but they are not available. And there are available tables, but no more free table. Not registering that memory for use. An estimate of how much memory is available for starting new application without swapping. Mem available can be less than mem free if there is no more reclaimable memory, like if it is all balloon out when using a hypervisor. Oh, okay. Do you mean better for using it as an estimate for remember to use when running new? Then yes. You have some mem free but zero mem available as I've seen. You can start any new process. Oh, interesting. If there is no more reclaimable memory, if it's a balloon out when using a hypervisor, then mem available it is certainly less than mem free. Maybe something like this. What is the difference between mem_free and mem_available in proc mem_info, I guess. Yeah, proc mem_info. Let me check here. Oh, I think it is on different manual page. An estimate of how much memory is available for starting new application without swapping. Available is an estimate of how much memory available is available for starting new user space application, I guess. Or maybe let's just call that application without swapping, and the mem_free have unused beta system. Is that correct? Let me check this. The amount of physical RAM in kilobyte. Oh, why is it different? Interesting. But from this main page, the sum of low free and plus high free. What is low free and high free? Amount of free low mem. What? And what is low mem? Is a memory which can be used for everything that high mem can be used for, but it is also available for the kernel used for its own data structure. Among many other things, it is where everything from SLAP is allocated. If I understand correctly, SLAP is some kind of case maybe for the kernel. I'm still not sure the term SLAP here. Mem is a memory above. Oh, physical memory. And mem_free is an estimate of how much memory we have. Maybe something like that. Memory above 860 megabyte. High mem areas are for use by user space program or for the batch case. Auto swapping, which means there is free memory, I guess. Okay, some other recommendable stuff. I've personally seen. Okay. No watermark. There is. Yeah, what is no watermark here? I am still not sure. We have or maybe not register. Yeah, I'm not sure. Estimating memory available for existing process. Any leftover memory is only for kernel operation. Oh. Yeah. I'm not sure if I get it's getting noisy. Okay. Is an estimate of how much physical memory we have. I'm not sure. I might need to analyze this more, guys. Okay. Well, let's continue this question 4 on the next session. So I guess that's it for now. Thank you for watching and see you next time. Bye bye.